Hello and welcome back to Calculus 3, where we explore section 12.7, tangent planes and linear approximations. So we are going to pretty much copy the same concepts from Calculus 1 when we did this. In Calculus 1, in the 2D realm, you have a function and the tangent line. Calculus 3, in the 3D realm, you are going to have a tangent plane. If you ever wondered what graduation hats mean, it's very simple. Just a tangent plane to your head. That's all it is. And as you tilt, I forgot I wanted to bring one in, and I forgot it at home. Every time I teach tangent planes, it's good to have it on. So, the graduation hat, you have the idea. As you move the graduation hat on your head, it is always tangential to the surface of your head. Now your head is round on top, unless you do the thing with hair, and you will have the tangent plane. You will have an understanding of tangent plane. So tangent plane has the equation as any other plane, which is that vector that gives us the orientation, the slope, right? And then x minus x0, y minus y0, and so on. Now, this being the tangent plane, it should come from the derivative, which means that our, what used to be normal vector ABC, is going to be now a vector of partial derivatives, which is the 3D gradient. So we are looking in vector fx, fy, and fz computed at the point of interest. So we start exploration by definition for this, and then do a few problems. So definition states, let f be differentiable at the point p0. Which is point A, B, C, with del f at A, B, C different than 0. The plane tangent to the surface fxyz equals 0 at p0 called tangent plane. Is the plane passing through P0 orthogonal to del f ABC, which is again P0. And it's very easy to see that the equation for this would be the dot product between these two entities. So you have your fx computed at ABC times x minus a plus fy computed at ABC times y minus b plus fz computed at ABC times z minus c equal to 0. So that's the tangent plane. Now, let's immediately compute one of these. That's very easy calculation. You just plug everything in. So here, tangent plane, let's define z. Actually, wait, that's the second one. Let's go with this. Your equation is given as, for the surface, as 2x plus y squared minus z squared equals to 0. And they want a tangent plane at the point 4, 1, and negative 3. So we are going to have our fx as 4x, fy as 2y, and fz as negative 2z. And then we just plug everything in. Fx will be computed at a, b, so that's 16. X minus a is 4. And then we have plus fz, we have 1 there, so that's 2, y minus 1. And then this is negative times negative is positive 6, z minus plus 3 equals to 0. And you see that's the equation of the plane. The derivative is 4x, and the value at which I'm computing the derivative x is 4, so I don't have any y's and z's in this case. So You go each one. Now we could push this to get it into 16. This is already fine, but you can do more if you want to. Plus 2y minus 2 plus 6z plus 18 equals to 0, which is 16x plus 2y plus 6z equals to negative 66. Is that 48? So you can have either of the two. You can leave this one, which is fine, or this one or the other. Tangent plane for z equals f of xy is given by z equals fx at AB times x minus a plus fy of AB, computed at AB, of y minus b, and then plus f of AB. That's another big formula. Now, if you are still trying to remember what was happening in Calc 1, let me just write it real quick. So in Calculus 1, what you had was the linearization formula, which you had as Lx was equal to f of a plus f prime computed at a x minus a. I can just hope that you see that here is these two, right? And then that one and that one. Now, where is the y term? Well, that's extra for another dimension for Calc 3. So that's technically the same thing if you are trying to draw the parallel to your Calculus 1. So you have your derivative in x direction computed at the point, which is the same what you had in Calc 1, and you had the function. Now, if you don't remember where the Calculus 1 thing is coming from, well, that's algebra formula y minus y1 is equal to mx minus x1, where this x1 and y1 are simply a f of a. So it all of this follows from the very basic algebra and just a simple upgrade upon the upgrade upon the upgrade, and we have a new application to what we can use it for. So you start with your point slope formula in algebra, this is elementary algebra, and then you say, well, I can figure out slope using the derivative, and now I can just do that in whatever number of dimensions I want. So it's a clear upgrade, progression from one to another. This is not, pulled out a hat by some magician. It's just this formula recast for 3D purposes. So we go from Calc 3 down to Calc 1 down to algebra. It's the same formula that is being recycled and just rewritten in a different way, different light, and used for. So now we are going to take a look at another example for homework, which is going to give us to practice that formula on top. So tangent plane, let's see, you're going to like probably, you like ease, right? That's the best. Oh, yeah. So z equals x squared times e to the x minus y. And you want a first or a second point? First or second point? Second point. Well,
checking at the end?
yeah.
Okay.
Okay. So we have the partial derivative of x. What do we have to do for partial derivative of x? Anyone? Product rule. Thank you for being present. So it's x squared and then e to the x minus y, and the derivative of that would be just 1, so that's it. Plus, copy the second, which is e to the x minus y, and then derivative of the first, which is 2x. And we are supposed to compute this at -1, -1. So both of those would be 0, which gives us 1. So it's 1 minus 1. No, minus 2. -1 on the first derivative, right? Actually, this is a bad notation. fx computed at -1 would be that's 0, so it's 1, so the first one is 1, plus that's 0, so it's 1, and then -2, so -1 there. Now fy is equal to the derivative of this is just x squared e to the x minus y, and then a negative, and then fy at -1, -1 will be, that's a 0, so that's just -1. So we have our del of f at -1, -1 to be -1, -1. All right, fine. So as I'm writing the equation of the plane, z is equal to -1 times x minus plus 1, -1 on y, which is y again plus 1, and then plus the function computed at this, which is the third point, which is just 1. That's f of a, b. This point over here is your f of a, b. So z is equal to -x, -1, -y, -1, +1. Those will cancel. Z equals -x. Oh, move everything to the left now to get the equation of the plane in the way we are used to it. Move x, move y, leave z where it is, and then on the left hand side you just have -1 alone. Alex, what?
Sure, it's a really dumb mistake, but f evaluated -1, -1 is 1. I got -1. I don't know why.
1 squared, -1 squared is +1 times
Oh my
1,
God.
right? But that's the third coordinate on the point. You don't have to compute it at all.
Cool.
Of course, cool, it's math. The next order of business is the linear approximation. So if you remember from Calculus 1, if you wanted to take the square root of, let's say, 17, you would say that you can find the square root of 16, which was 4. And then what you can do is you can actually linearize here and then compute that 17 in a tangent line rather than the square root. So if this was it doesn't matter. The tangent line, as you can see, is almost the same as the function. So we computed 17 in the tangent line rather than in the square root because it would be easier. So we would assign f of x to be square root of x, and we would find the derivative, which would be 1 over 2 root x. And then we would use 16. So for linearization, we would say f of a, which is 4, plus the derivative computed at this, which is 1 over 8. And you would have x minus a, which is, again, 16. So we were computing 17 now. We would say that the square root of 17 was actually L computed at 17, which was 4 plus 1 over 8. And then you had 17 minus 16, which would be just 4 and 1/8. Now 1/8 is 0.125. So this was equal to 4.125. Now if you take the calculator and check the square root of 17, you would see how good this actually is. So the calculator gives us that the square root of 17 is approximately equal to 4.123, 105, 626. So we are 0.2 of a cent off with our calculation, and we computed everything in a tangent line, because this is the tangent line here, linearization. That's the tangent line, because if you move this 4 to the other side, you get your y minus y1 slope, right? And so the idea of linearization, which today pretty much we don't need because we can compute anything using technology, but the idea of linearization is to bypass the difficult things to compute like trig and ln and square roots and cube roots, and replace those calculations by computing in the tangent line or the tangent plane. Because you see how tangent plane looks like this: x plus y plus z equals to -1. So you plug in the values and you can compute easily. So for linear approximation, we are going to do the same thing. You are trying to compute a surface that is not too fun. What you do is you linearize it and come up with a tangent plane that is centered close to the plane that you were looking at originally, to the point that you were looking at originally. And then you compute the point that you need to compute in the tangent plane rather than the function, because that was annoying. So to take a look at one of those examples, we have trying to find something that it's nice. All right, they're all equally nice. So problem 29 says that the function, the surface, right, is given by z equals, or f of x, y equals, ln of 1 plus 0 plus 0. And they want to compute 0.1 and negative 0.2. So obviously today's day and age, you plug these values here and you take the calculator and you hit the ln button and you're done. But let's, go just 50 years ago. 50 years ago, that was not available. So what we do is we find the tangent plane at 0, 0, because 0, 0 is close to our point and easy to compute. And we find the tangent plane at that spot. So I'll need fx, which is, why did I write 1 plus 0 plus 0? I was supposed to write 1 plus x plus y. Whoa. So we find fx, which is 1 plus x plus y, and then 1 on top, and fy, which is again 1 over 1 plus x plus y. So these are the derivatives, partial derivatives. And we now compute our tangent lines z is equal to, we compute 0, 0, so this is just 1. We get x minus 0. I guess I'll put 1 there as well. And then plus, this is also 1. And we also have y minus 0. And then to compute 0, 0, ln of 1 is also 0. So we have plus 0. Wow. So the equation, the z equation plane is z equals x plus y. That's all it is. So that's the tangent plane. At 0, 0. Now 0, 0 is obviously sufficiently close to what we have to compute. So I will say that ln of 1 plus 0.1 minus 0.2 is approximately the same as just 0.1 plus negative 0.2, which is the formula up there, negative 0.1. Now again, you can verify on your calculator how much is ln of 0.9, because that's what you are trying to compute actually. So ln of 0.9 is negative 0.1053, so we are about 4.5 tenths of a cent away from the good answer. So approximations are there to give us possibility to compute values of a function easy, but it's approximation, so they're not exact. Right? You can get much better result using a calculator or a software of some sort. And for the most part, we don't use this at all because we have computing power in cell phones and everywhere else except in the head. Right? That has been vacant for some time. So try a few problems at home, obviously for homework. Next week, we are going to finish off the chapter. The quizzes are supposed to start tomorrow, right? So set your alarms for 5:37, and quiz starts at 6. See you all at next week. Bye, stream.